Okay, so far in our studies we've covered the test for divergence for an infinite series, which is if the limit as n approaches infinity of the terms is not equal to 0 or it does not exist, then the infinite series is divergent. So this test confirms if the series is divergent, but, it's a big but, if the limit as n approaches infinity of the term a sub n is equal to 0, then the infinite series may or may not be convergent. So we can't conclude that a series is convergent if the limit of the terms approaches 0. And we've covered this now extensively. So for example, the harmonic series, which is the sum from n equals 1 to infinity of the terms 1 over n, well, the limit of the terms as n approaches infinity of 1 over n is equal to 0, but the series is divergent. So how do we know that the series will be convergent or divergent then? Is there a test for this? And the answer to that is yes. It's called the integral test. And we're going to show how this integral test works in this video. So let's consider the series, the infinite series, the sum from n equals 1 to infinity of 1 over n squared. So with the terms here, let's look at the corresponding function. We're going to let the function f of x equal 1 over x squared. Okay, let's write out the first few terms. So we've got 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared plus so on and so forth. So let's have a look at the chart of the function 1 over x squared. So here's a plot of f of x equals 1 over x squared. Let's consider the area between x equals 1 to x equals 4, the area under the curve. We'll call this A for area. And we know from calculus we can find the area by integrating from x equals 1 to x equals 4 of 1 on x squared with respect to x. Just write that as the integral from 1 to 4 of 1 over x squared. So the integral is negative 1 on x, bounded by 4 over 1, which equals negative 1 on 4 minus negative 1 on 1. And we can rewrite this as 1 minus a quarter, which gives us an area of 3/4. Alright, so that's pretty straightforward. Now let's write out the first few terms of the series again. So we have the series from n equals 1 to infinity of 1 over n squared, which equals 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared. Let's go to the term 1 over 4 squared plus dot dot dot. So we'll represent each of these terms as rectangles under the curve of 1 over x squared. Let's switch off the area A for now. This is 1 over 1 squared. We'll do the other terms in a different colour. So the second term is 1 over 2 squared. We've got 1 over 3 squared for the third term. And 1 over 4 squared for the fourth term. So let's label these 1 over 2 squared, 1 over 3 squared, and 1 over 4 squared. So the addition of these rectangles, A2 plus A3 plus A4, we can see if we switch the area back on, is going to be less than or equal to the integral from 1 to 4 of the function f of x, which equals 3/4. Alright, so that makes sense. So that implies then if we add the first term, Let's put that in a different color, A1, and then plus the rest, A2 plus A3 plus A4 is going to be less than or equal to A1. So we're just adding A1 to both sides of this inequality of the integral from 1 to 4 of the function f of x with respect to x. But if we keep adding rectangles, this inequality still remains true. So if we were add up to the nth term and we extend the integral to x equals n, alright, so we extend the area under the curve to x equals n, so we change the bounds of the integral from x equals 1 to x equals n. This inequality still holds true, because all of the additional rectangles will still have an area less than the area under the curve. And the addition of these terms here, a2 to an, we can write as the sum from I equals 2 to n of 1 on n squared. So on the next line, a1 plus the sum from I equals 2 to n of 1 over n squared is less than or equal to a1 plus the integral from 1 to n of 1 over n squared with respect to x. And we'll write this more generally, in more general terms, as the sum from I equals 2 to n of a sub n, and more generally the integral as f of x. So on the left hand side of this inequality, what this is the partial sum to the nth term. So the partial sum to the nth term is less than or equal to the first term a1 plus the integral from 1 to n of the function f of x with respect to x. Now here's the really cool part, because if we take the limit from n to infinity of s sub n, this will be less than or equal to the limit as n approaches infinity of the right side of the inequality. So the limit from n to infinity of s sub n is the series. So we write this as the sum from n equals 1 to infinity of all the terms, and that's less than or equal to the limit as n approaches infinity of a1 plus the limit as n approaches infinity of the integral from 1 to n of f of x dx. a1 is independent of the limit, so we can just get rid of the limit in front of that. And the limit from n to infinity of the integral just forms a improper integral from 1 to infinity of f of x with respect to x. So in our case, the sum from n equals 1 to infinity of 1 on n squared is always going to be less than or equal to the first term, which is 1 over 1 squared, plus the improper integral of 1 to infinity of 1 on x squared. So let's see if this improper integral is convergent. The integral from 1 to infinity of 1 on x squared with respect to x is equal to negative 1 on x bounded by infinity on 1, which equals negative 1 on infinity minus negative 1 on 1. So we have 0 minus minus 1, which equals 1. So this improper integral is convergent because it evaluates to 1. So the series then is always going to have an upper limit. So the series of 1 on n squared is going to be always less than or equal to 1, which is what a1 is, plus the result of the integral, which is 1. So the series is always going to be less than or equal to 2. And therefore, the series is convergent. Okay, so let's now compare this to the series, the sum from n equals 1 to infinity of 1 over the square root of n. And expanding out a few terms, we have 1 on square root 1 plus 1 on square root 2 plus 1 on root 3, plus so on and so forth. Let's let the function, the corresponding function f of x, be equal to 1 on the square root of x. So a chart of this function is shown here, where the curve is the function f of x equals 1 on the square root of x. This time I'm going to draw the rectangles that corresponds to the terms of the series. I'm going to draw the rectangles above the curve. So here we have 1 on root 1. And subsequently we've got 1 on root 2, 1 on root 3, 1 on root 4. So from this chart we can see when we add up the first n terms, so a1 plus a2 plus a3 to ... plus a sub n, because we have drawn these rectangles above the curve, this is going to be greater than or equal to the integral from 1 to x equals n of the function f of x with respect to x. And the left hand side of the expression can be written as the sum from I equals 1 to n of a sub n is greater than or equal to the integral from 1 to n of the function f of x dx. Okay, so the partial sum to the nth term is going to be greater than the area under the curve to x equals n. So again, we can apply the limit. So the limit from n to infinity of the partial sum is greater than or equal to the limit from n to infinity of the integral from 1 to n of the function f of x. And of course this expression is simply the series then. So the series, which we express as the sum from 1 to infinity of a sub n, is going to be greater than or equal to the improper integral from 1 to infinity of f of x with respect to x. So in our case, specifically for us, we've got the sum from n equals 1 to infinity of 1 on the square root of n, and that's going to be greater than or equal to the improper integral from 1 to infinity of 1 on x squared with respect to x. Sorry, 1 on the root of x with respect to x. So let's evaluate this integral on the right hand side. The integral from 1 to infinity 1 on root x dx is equal to integral from 1 to infinity of x to the negative half, x to the negative half power with respect to x. And we can simply use the power rule for integrals here. So we've got x to the power of a half, so we add 1 to the index divided by the new power, and that's bounded by infinity over 1. And of course we can write that as 2 by the square root of x bounded by infinity to 1. So we've got, evaluating this, we've got 2 by root infinity minus 2 by root 1. This integral then we can see is divergent because we can't really evaluate what this is, but the square root of an infinitely large number is still going to be an infinitely large number minus 2, which is still equal to an infinitely large number. So this improper integral is divergent. So therefore, the series sum from n equals 1 to infinity of 1 on root n is going to be greater than or equal to a divergent improper integral, and therefore the series is also divergent. Okay, so after showing how it works, we are going to define the integral test. Of course, the integral test is for the convergence or divergence of a series. Of an infinite series. So if we have a continuous function, and it's continuous from x equals 1 to x equals infinity, so it's continuous on x equals 1 to infinity, the terms of a series a sub n is equal to f at x equals n, and the function is positive and decreasing on the interval. So let's write the word if. So if a function is continuous on 1 to infinity, the term a sub n is equal to f at x equals n, and it's positive and decreasing on the interval. Then the series sum to infinity of a sub n is convergent if the improper integral from 1 to infinity of f of x with respect to x is convergent, and the series from n equals 1 to infinity of a sub n is divergent if the improper integral from 1 to infinity of f of x dx is divergent. So let's box this rule for future reference. And that shall do it for this video. If you've been able to make sense of it, smash that like button, subscribe, share with all your classmates. Got any questions? Let me know in the comment section below. Best of luck with your studies, and I'll see you on the next video.